Hello everybody, this is Dr. Christopher White and welcome back for part 3 of Sedimentary Rocks part 2. So before we go any further, let's just get the code word out of the way. The code word for this presentation is dragon. I repeat, dragon. D-R-A-G-O-N, like the mythical creature. So that was dragon. So please make sure you write that down and put it somewhere safe because you're going to need it for the code word quiz. Okay, so in the previous video we just finished off talking about some of the most important terrestrial depositional environments, and now we're going to move on to the transitional depositional environments. So these types of depositional environments include deltas, beaches, barrier islands and lagoons. So once again, just like we just did with the continental environments, we're going to go through these sub-environments. We're going to look at some of the features that we would expect to see in the sediments deposited. Okay, so let's start with deltas. So a delta will form when a stream or river, so a fluvial system, enters a body of water. So that body of water can be small, it can be a lake, in which case you'll typically get what's called a simple delta, or it can be a slightly larger body of water, in which case you will, like an ocean or a sea, in which case you'll get a more complex delta. The reason for this is that the type of delta you get will vary depending on the conditions. So a lake is a more protected environment, so the delta you get will tend to be more simplistic. In contrast, an ocean or a sea, obviously it's a larger environment, bigger waves, tidal effects, that will rework your delta, making it more complex. So your deltas will be affected by a mixture of different processes, of which waves and tides are arguably the most important. So simple deltas are subdivided into three main layers: the bottom set, the foreset, and the top set. So the bottom set forms ahead of the delta. So if I just skip to the next slide, here's our imagined situation. So here's our land, and here's our delta. So as the river is bringing the water and the sediment across the delta, obviously it gets deposited at the delta edge. So obviously at the delta edge, the heavy stuff gets dumped first. So you're going to get the sands being deposited, the silts, but the water that contains the clay is actually going to continue out in front of the delta for quite a large distance. Okay, because remember, this is fresh water. So it's fresh water entering salt water. Salt water by its nature is more dense, and so the lighter fresh water will naturally move across the surface of the ocean some way out to sea. And so when it's all the way out here, it'll come to a stop, and that's when the clay starts to get deposited. So your bottom set beds will actually be well ahead of the visible edge of your delta. So you might think your delta actually starts here, when in reality it's actually starting much further out to sea, because this clay-rich water is being transported across the surface, and it's not depositing the clay until quite a large distance in front of the delta. So that's our bottom set. It mostly consists of clay, maybe a little bit of silt, and obviously because the clays are raining out slowly onto the seafloor, you tend to get a laminated mudstone. The mudstone will be biatubated though, so there'll tend to be quite a few burrows in it, mollusk burrows, that kind of thing. Now over the top of the bottom set beds we have the foreset beds. Now this represents the main mass of the delta. So it's a mixture of silt and sand, which is being deposited by the river as it enters your body of water, be it your lake or your ocean. And so if we just go to this slide here, essentially what we're looking at is the foreset beds are being deposited right there, and essentially it's the material that's being dumped underwater, and it forms this area here, which is going to be our foreset. Okay, now that's going to make up the vast majority of the bulk of our delta. So it's going to be stratified, so you're going to have a sequence of beds, and once again there will be biatubation. It will be burrowed, there'll be animals like mollusks and sea urchins, for instance, that will be burrowing through the sediment. Now the top set is distinct from the foreset in that it is mostly dominated by sand. Now the reason it's dominated by sand is because the top set, as the name suggests, is the top part of the delta package. That means it's exposed to the action of waves and tides. And so what will happen is the very fine material, your silts and clays, will naturally be stripped away and pulled out to sea by the waves and by the tides. This means the sand gets left behind. And so what you end up with is you end up with this layer at the top of your delta that's very sand rich. It contains ripple marks, so we get symmetrical ripples, and once again we get biotubation. We may also see channel deposits cutting across the top set. Now we can distinguish the channel deposits because of course they would have asymmetrical ripples. So if we go back to our diagram here, these areas, like this area here for instance, would be affected by waves, and so that would give us symmetrical ripples. The channels here, well they are a unidirectional flow, so the water's only going in one direction, so they would give us asymmetrical ripples. So we can distinguish between our different environments, between the sandy topset beds and the sandy channel fill. And so what we end up with a sequence of sediments that goes from clays down at the bottom into a mixture of silts and sands in the middle and sands at the top. So we have an upward coarsening sequence. Okay, so we have an inversely graded sequence. And so what will happen over time is our delta will naturally build out. So here I have a pretty crude diagram, but I hope it will get the point across. So here's our land, here's our sea, here's the seafloor, and this represents the delta. So we have the bottom set in yellow, the foreset in peach, and the top set in blue. And so over time, as more material gets dumped in front of our delta, it will steadily grow out into deeper water. And this process of our delta building out into deeper water is called prograding. Okay, so there we go. So our delta will build out into deeper water, it will prograde. So in terms of the bottom set beds, it will very commonly contain marine fossils, lots and lots of biotubation. The top set beds, on the other hand, can often contain land fossils. So we'll expect to find the fossils of land animals, and we might even find root casts as well, which would suggest that some parts of the delta may spend almost all of their time above sea level. So unlike lake deltas that present a simple morphology, marine deltas are more complex, as I said, because a marine delta is being reworked by waves and tides. And so this is going to produce a far more complex appearance. So marine deltas are split into three main groups based on the dominant modifying process. So there are fluvial systems. So these are deltas where the river itself is depositing so much sediment into the system that waves and tides are not powerful enough to get rid of it. So what happens is you end up building up more and more and more sediment. And this will produce a type of delta which is sometimes referred to as a bird's foot delta, but it's more commonly known as a stream or river dominated delta. If your delta is primarily controlled by the redistribution of sediment by waves, then it is a wave dominated delta, and if the sediment is mostly distributed by tidal forces, it is a tide dominated delta. So I'm sure we're all familiar with this delta. This is obviously the Mississippi Delta right here. It's the classic example of a river-dominated delta. And so what we have here is we obviously have the Mississippi River coming along, and it's depositing huge quantities of sediment into the Gulf. There's so much of it, in fact, that the waves and the tides can't get rid of it fast enough. So it just keeps building up, building up, and building up. And so what's happening is the delta is literally building out into the Gulf. So every time your delta deposits more sediment, it's building out the coastline a little bit more each time. And so over time, as your delta deposits more material in front of itself, it's literally creating new land for the Mississippi River to go across. And so you can see, so this is actually the area either side of the main channel itself where sediment's being deposited, producing new land, and obviously that then allows the Mississippi River to continue out into open water. And obviously this is the active delta edge right here. So you can see all of this cloudy sediment around the delta. This is all your silts and your clays coming out of the water. And so what we have here, this green area, this would be your top set. These kind of more white colours, this would be the area in which your foreset is being deposited. And out here in the deeper water, out here is where your bottom set beds are going to be forming. Now, in the case of wave-dominated deltas, the thing that's controlling the shape of your delta is wave action. And the classic example of a wave-dominated delta is the Nile Delta. So obviously Nile River comes up, cuts through Egypt, and it makes it onto the south coast of the Mediterranean Sea. In terms of the coastline itself actually, if the delta wasn't there, would come up like so. It would actually come down a bit, and then it would come back up on the other side. It would form a natural protected inlet right there. Obviously, because you have this very large river, you've got the Nile, which obviously moves huge quantities of sediment. That sediment obviously has filled up this natural notch in the coastline, and the delta has steadily prograded out until it's become level with the coastline. Now, once it's become level with the coastline, what's happened is any new sediment that gets deposited on the active edge will then get transported away by the waves. So if we just look down here, we can see this map is a map showing you the prevailing wind directions for the Mediterranean Sea. Obviously, the Nile Delta is right down here. And so what we can see is the prevailing wind is coming from the northwest, coming down towards the southeast. It hits the Egyptian coast, and then it turns and comes up past Israel, Lebanon, and up towards Syria and Turkey. And so what you have is you have waves. So the wind is coming in from the northwest going southeast. Those waves are hitting the coastline and then naturally pushing the sediment along the coastline. Okay, so up past the West Bank into Israel, then up into Lebanon, Syria, until eventually it goes all the way up here until the Syrian-Turkish border. So the sediment gets transported all this way simply by wave action. And obviously, the action of the wave stops the delta getting any larger. So you've reached a point of equilibrium where the amount of sediment being deposited is equal to the amount of sediment being removed by the waves. Your final type of delta are your tide-dominated deltas. So the classic example of a tide-dominated delta is the Ganges Delta. So we tend to get tidal-dominated deltas forming in slightly more sheltered regions where wave action is a little bit more reduced. So in terms of the Ganges Delta, it's actually protected by India to its west and the Thai Peninsula to its east, so that helps to give it some degree of protection. In terms of what's actually going on, well, the Ganges Delta actually gets mostly covered by water every high tide. And so what will happen is your delta will get covered over by water, but the thing about the rate of tidal retreat in the Ganges area is that it's quite fast. So the sea level goes up quite fast and it drops down quite quickly as well. And so what will happen is your water will naturally exit your delta quite fast. And as it exits the delta, it pulls sediment off the delta into deeper water. The other thing that the movement of the tide off the delta and into deeper water will produce is it will produce these channels, these distributary channels. And the interesting thing is about them, if you look at the orientation of them, you'll notice that they are approximately orientated parallel to each other. So the orientation of these channels will match that of the tidal current. So as we can see, the channel is orientated approximately north-northwest, south-southeast, and so that's going to be the primary tidal current as well. And so all that's happening here is the main thing that's shaping your delta is simply the tidal processes. Okay, so deltas are actually quite straightforward. So now we're going to think about barrier islands. So a barrier island essentially is a very large linear body of sand that builds up off a continental margin. So the island in question will develop parallel to the shoreline, but it will be separated from the mainland by a lagoon. And barrier islands are particularly common along the Gulf Coast and the Atlantic coasts of North America. So if we just skip to the next slide, we can actually see some examples of some barrier islands here. So these are the barrier islands associated with the Louisiana coast. So you can see here's our coastline there. Here are lines of barrier islands here. Here's the Mississippi Delta just over there. And you can see this area that separates the barrier island from the mainland is going to be our lagoon. Now in this case you'll notice the lagoon is able to communicate with the larger Gulf of Mexico quite easily. There's some very large gaps there. But let's compare that to Long Island in New York. So obviously here's our landmass and here is our barrier island along the front there. And so this area here, for instance, represents our lagoon, separating our barrier island from our mainland. In this instance, you'll see it slightly different. You'll notice that there's not much communication between the Atlantic Ocean out here and the lagoon here. So this lagoon is going to be quite protected. So it's going to be its own little distinct environment. The other thing you'll notice is that sediment that's being deposited into this lagoon is slowly filling it up. So this, if given enough time, this lagoon will completely fill up with sediment, at which point it's described as having silted up. So when we observe barrier islands in the rock record, we see them as elongate sand bodies, if we're thinking about them in 3 dimensions, that we're running parallel to the coastline. But then you have to think to yourself, well, hold on a minute, how can we distinguish that from a beach? Because a beach is also a elongate sand body that runs parallel to the coast. So the way that we can separate the barrier island from a beach environment is simply by the presence of the lagoon. So if we see a situation where we have a linear elongate sand body and a lagoonal environment directly behind it, we know this linear sand body must be a barrier island. If, however, there was no lagoon there, we would have to assume it was probably just a beach. So barrier island systems will actually have several sub-environments. There's the beach sands, the dune sands, and the lagoon deposits. So here are 3 different subunits, and here's a diagram that's going to hopefully help us to see what's going on. So the first one of our environments are beach sands. Now, when we're discussing the beach sands in terms of a barrier island, the same criteria goes for a regular sandy beach as well. Okay, so what I'm about to describe not only describes the beach sands of a barrier island, but also your average normal sandy beach. So what you've got is you have a build-up of sand that's exposed to the sea or the ocean. So it's going to be on the seaward side, which means it's going to be reworked by wave action. So you're going to have a situation where you're going to get lots and lots of symmetrical ripple marks forming, because you have bidirectional flow. The water comes up the beach and then comes straight back down the beach back into the ocean basin. In terms of the sediments that we have, well, most barrier island sediments and most beach sediments in general are sand dominated. That's simply because as the wave hits the beach, it picks up silts and clays and then pulls them back out into deeper water. So it gets rid of the silts and clays, but larger stuff like gravels, cobbles and boulders were never part of the system in the first place. They were too big to be in this area. So essentially all that gets left behind is the sand. Now, if you're in an environment where you actually have very, very powerful waves, those waves can actually be powerful enough to remove the sand as well. And if that happens, what you'll get is a beach which is dominated by gravels and cobbles instead. So a beach by its very nature doesn't have to be sand dominated. You can also have beaches made of cobble-sized clasts and gravel-sized clasts, but the vast majority of beaches will be sandy. So we can obviously distinguish between these beach sands and the types of sands you would get in, let's say, a desert environment by the fact that these beach sands will contain shell fragments mixed in with the clasts. Now, on the back side of our barrier island, so the part of the barrier island that's protected from the waves, we are going to form what's called the dune sands. So the dune sands are on the landward side of the barrier island. Once again, it's a sand-dominated regime. However, in this instance, because the sand is protected from wave action, if it's being moved around, it's being moved around by the wind. And so this means in the dune sands, you're going to have dunes forming and ripples forming. So you're going to end up forming a layer of very sandy sediment, which will display cross-bedding and asymmetrical ripple marks. So once again, you're thinking, well, hold on a minute, what I've just described there could match the type of sediment that we could get in a desert as well. How do we tell the difference? Well, once again, we would have shell fragments in our barrier island dune sands. So that would help us to distinguish between this type of sediment, this type of sandy deposit, and the type of sandy deposit we would get in a desert system. In terms of the lagoon is typically a semi-isolated body of water, so it's a relatively protected environment, and in terms of the energy of the system, it's normally quite low energy. So this means that any water in the lagoon environment tends to be quite still. And this obviously means that if you have fine sediments like silts and clays, they will be able to exit suspension and fall out onto the bottom of the lagoon. So this means that most lagoons are mud dominated because we have the river bringing a mixture of sandy and muddy sediment, Obviously, the river sediment that's deposited out here, while the silt and the clay gets pulled out into deeper water, leaving the sand behind. But back here in the more protected lagoonal environment, you don't have that wave action getting rid of the mud, so the mud builds up over time. So you get essentially a sediment that's dominated by silt and clay with a little bit of sand mixed in there as well. In terms of sedimentary textures that we might see, we would expect to see laminations because the clay and the silt is raining out slowly onto the lagoon floor. And we would also expect to see quite large amounts of plant fossils, because a lot of lagoons tend to be very good environments for plant growth. So just think of swamps like the Florida Everglades, the classic example of a lagoonal environment. So there you have an isolated lagoonal region that's protected from the Gulf of Mexico. The lagoon itself has got lots and lots of mud in it, and it's become very, very heavily vegetated. So it's not uncommon at all to find copious quantities of plant fossils within these lagoonal muds. And if you have enough organic material building up, it can actually eventually be turned into coal seams. So lagoonal deposits are actually very commonly associated with the buildup of coal. So if the sediment influx is high enough, or the degree of tidal erosion low, over time mud will build up in the lagoon and eventually it will silt it up. So it'll just completely fill with sediment and the lagoon will be lost. Now, in terms of the lagoon itself, lagoon conditions vary. So obviously if your lagoon is able to communicate with the larger body of water quite easily, like we can here, obviously that means the water back here in the lagoon is going to be pretty much the same as the water here in the Gulf of Mexico. However, in instances where our lagoon is isolated from the larger body of water, it's actually going to start to take on its own distinct composition. So if we look at this area here, for instance, you can see we have these short rivers which will be bringing in fresh water into the lagoon. However, there won't be much salt water coming in. And so this means this particular lagoonal environment is going to be more fresh water than salt water. So the salinity of the waters in the lagoon will vary depending on how much communication there is between the lagoon and the open ocean. Obviously this is then going to have an effect on what types of organisms you get living in your lagoon. And a good geologist will be able to look at the organisms and they'll be able to gauge, how saline was the water in the lagoon. Now, if your lagoon becomes fully separated from the sea and the influx of fresh water is low, the lagoon water will eventually begin to evaporate away, and we can see that happening here. Okay, so this is a lagoon off the coast of Tunisia, so this is the Mediterranean Sea over here. And what you'll notice is here's the lagoon, there. Here's the river coming into it. There's actually another river that comes up here just slightly out of shot. And in terms of the lagoon itself, the only way that the lagoon can communicate with the open ocean is there. But you'll notice though they've actually gone and built some structures in the way to isolate the lagoon. And so obviously what happens is during the spring you'll have water coming in, the lagoon will fill up, and you can see here this is the lagoon looks quite muddy, but there is obviously water in it in this half of the image. But you can see at this second half over here was taken at a different time of year, probably in the summer. And you'll see that a lot of the water has evaporated away, and you've got the evaporites here as the kind of creamy white, and what's left of the lagoon is visible right there as this darker patch. And over time this would evaporate away, just leaving behind evaporite deposits as it went. And of course, depending on the salinity of the water, you would get different types of evaporite. So if your water was fresh, you would expect to get minerals like gypsum forming, maybe a little bit of halite, and you would expect to get minerals like borax or epsomite forming, so boron minerals, very commonly associated with the evaporation of fresh water. If this was a more saline lagoon, so it had more of a seawater-like composition, you would expect to get gypsum forming, some carbonates forming, and you'd also expect to get a lot of halite forming, because obviously there's a lot of salt in salt water. So, depending on what type of water you're dealing with, you're obviously going to get a slightly different evaporite makeup. So the final environment we're going to think about are tidal flats. So tidal flats occur in areas of coastline which are periodically covered by seawater at high tide and then exposed at low tide. So these are mud-dominated systems, so there's lots of clay, lots of silt, and lesser sand. So this sediment, which is mud-dominated, is deposited typically into a sheltered coastline, either by rivers or by wave action, because most of the time by rivers, but sometimes what will happen is muddy sediment will actually be moved up to the coast by waves until it eventually enters some kind of protected notch in the coastline, at which point the muddy sediment will build up. Tidal flats do not have bottom set, foreset and top set morphologies like deltas, so they are distinct from delta environments. However, like delta environments, most tidal flats will prograde seawards. They will build out into open water. So the tidal flat sediments present a distinctive texture which is referred to as herringbone crossbedding. And this is when you have different sets of small crossbeds. One set goes, let's say, dips down to the bottom right, and then the next set will dip down to the bottom left. And so the fact they're dipping in opposite directions shows us what we have are two different unidirectional flows. So one unidirectional flow is when the tide comes onto the tidal flat, so the water's moving in just one direction. That gives you a set of asymmetrical ripples going one way. But then about 12 hours later, the tide reverses and the water heads back off the tidal flat, so you get a unidirectional flow in the opposite direction. And that will produce a set of asymmetrical ripples dipping the other way. Don't panic if you didn't understand that. There's a picture coming up which will make it clearer. So in terms of tidal flats, here's one of the classic examples. This is Morecambe Bay in the United Kingdom. So you can see here's the coastline coming along here, continues over there, and you can see we have a natural protected area right here. And you can see we have two rivers coming in, one there and one there. So if we look at it in terms of the Ordnance Survey map here, here's one river coming in, here's the other river, this headland here is this area here, this area over here is there, and this area over here, Morecambe itself, is this town right there. And so this is what it looks like at high tide, and this is what it looks like at low tide. So you'll notice it's a very silt and clay rich sediment with lesser amounts of sand. So in terms of what we see, if we look at our our stack of tidal sediments, what we're going to get is we're going to get a sequence that typically consists of more sandy material at the bottom and muddier material at the top. So the reason for the fact that this being more sandy is this is the area that's exposed at the mean low tide. So at low tide, sea level is going to be right here. And that means this area of your tidal flat is going to be being constantly hit by wave action. And so those waves are hitting the sediment, and obviously as the wave returns into the open ocean, it's pulling the clays and the silts with it. So you just get the sand left behind. And the same goes for the tide as well. When the tide goes out, it will also take a lot of the clay and the silt with it. And so this means sediments that have been present in the tidal flat for longer periods of time will have the clays and the silts stripped away. And so these older sediments which sit deeper in the stack will have had more time to be reworked, and so they will be more sand rich, I do apologise. The sediments towards the top of our stack, well, they're only really exposed to the action of the waves as you approach high tide. And so this area is not worked by the waves quite as much. So this obviously means you have more mud being retained. Plus, you actually have new mud constantly being added as well. So this area here is, has less loss of silt and clay and a constant resupply of silt and clay coming in as well. So that means this area here is naturally going to be muddier. In terms of the types of sedimentary structures that we see on tidal flats, the one we're looking for is herringbone crossbedding. So if we look over here, we can see a picture of some herringbone crossbedding. So if you look here, you'll see we've got a set of crossbeds that are dipping down like so, in that direction. Then the next set of crossbeds are dipping down in the opposite direction like so. This set is going down like that, like that, like that. So essentially we have a zigzag pattern. It goes this way, that way, that way, that way. And so one set of these crossbeds represents the tide coming onto the tidal flats, and the other set of crossbeds represents the tides leaving the tidal flats. It's not uncommon for previous sets of crossbeds to be destroyed when the tides ebb and flow. So you're not going to get a beautiful, complete pattern. You know, it might look a little bit more chaotic. So if we look at this picture here, you can see once again we have a lovely set of herringbone crossbedded sandstones. You can see the crossbeds quite clearly, and thankfully the person that actually produced this image has very kindly marked out the crossbeds and also the direction of sediment travel, the paleocurrent. So you'll see that what we have here we have a set of beds. You can see, for instance, you know, the tide came in, the tide went out, the tide came in again. Now you'll notice in this case we've lost a couple of sets of the crossbeds related to the tide going out. When the tides come in, tide goes out, comes in, etc. So each one of these sets of crossbeds represents the tide coming in or the tide going out. And so we get them because these tidal flats are tide-dominated areas. It's the tide that's really moving the sediment around. Wave action is, on the whole, of much lesser importance. So just bear that in mind. So when you see these multiple sets of crossbeds stacked one on top of another, the first type of environment you should really think of should be tidal flats. You know, it should really scream at you that, you know, that's what you're looking at. So to finish, this is the table from the textbook. So far we've been through continental environments and transitional environments, and in the next presentation we will be looking at marine environments and interpretation. Okay everybody, thank you for listening and have a good day.